Right, recording is rolling. Friday, December 10th. So, a bunch of guys turned in your Chapter 8 questions. You guys remember rotational dynamics quiz due Monday? A lot of you guys have already turned this in. Had that a while, but there. And we're going to continue this midterm review. All right, so I got to a slightly different place with each class yesterday. You guys remind me, I think we were somewhere in the mid-20s. Did we do Girl Hanging from the bar?
I think we've just finished linear.
We just finished 18.
18? Oh. Huh. That's, okay. I didn't realize that. It's a little bit behind. Okay, yeah, let's do it. Right, so cannonball is fired into frictionless space. Tell you what I have to do. I have to keep a little bit of a fast pace, so yeah. Get you guys caught up here there. The amount of force required to keep it going is, well, we're talking about, what's the answer to that? Isn't this the Voyager spacecraft question? How much fuel does the Voyager spacecraft need to stay in motion? None. There's no force needed. It's only moving because of inertia. In fact, if it slowed down, you'd have to have a force to slow it down too, just like you need a force to speed it up. But just to keep going, just inertia, no force. If the force of gravity suddenly stopped acting on the planets, they would, here, show you guys a picture. You guys tell me which one is the correct answer. Okay, so, sun, here's the orbit of some planet. Put a planet P right here. Okay? And you can take this roller. Notice I'm holding this roller flush to the curve, like flush. Okay. So that will show the direction of its instantaneous velocity. Like right here, it's moving instantaneous velocity, something like this. Okay. It's changing the direction of its velocity because there's a gravity force pulling in, acting as a centripetal force. Okay. But suppose you turn that off. What if the planet gets right here? It's moving this direction at this speed, and then say, turn off gravity right at that moment. Does the planet continue moving in that direction, or does it make a random 90-degree turn to start going straight away from the sun? Which of those is correct? Yeah, tangent to its motion. Just keeps going that way. That is also a law of inertia, isn't it? So tangent to its motion. Good call. A sheet of paper can be withdrawn from under a container of milk without toppling the container. If the paper is jerked quickly, this can be done because that container milk has a lot of inertia or a lot of weight. Which property lets the milk container stay in place? Has a lot of inertia. Okay. Now, inertia and weight would be directly proportional, but specifically the inertia property that lets the container stay in place. So that more weight doesn't help by itself because more weight would put more increase the friction force, which would make it more likely to topple, but more inertia, yeah, more tendency to stay right there. You guys remember the tablecloth trick with Paul Hewitt? All those Paul Hewitt demos, they are in a zip folder on Google Classroom if you want to access those. That could probably be good review material there, right? I showed you some of his videos, but not all of them, but you want to watch them, they're there. The force required to maintain object at constant speed in free space. Hey, we just talked about this one. How much force? 0. No force. Right? If it's just going, it's just going. Right? If it did have a force, it would either speed up, slow down, or change direction. But yeah, just constant speed, constant velocity, deep space, no force. Equilibrium. Let's see, is it when all forces on an object are balanced? Ooh, that sounds good. The sum of the forces in the positive x direction equals the sum of the forces in the negative x direction? That sounds good too. The net force on the object is 0? Yep. The sum of the forces up equals the sum of forces down? Yep. This looks like all of the above, doesn't it? Tell you what, just in the last few weeks, we actually added one more condition to this list for equilibrium. And what was that? What else also has to zero out? The torque. Yeah, the torque. Yeah. Right? And that was particularly useful for answering questions like this next one. Girl whose weight is 500 newtons hangs from the middle of a bar supported by 2 vertical strands of rope. What is the tension in each strand? Now, this is one of those questions that you can probably figure out just at a glance by looking at it, but there's more than I want to say about this one, so let's get this going. We got girl hanging from middle of a bar and supported by 2 vertical strands of rope. So we've got her weight as being 500 newtons, so going to do sort of like free body diagram style. Like 500 newtons of weight, 500 newtons of force. Okay? Now, if she's hanging right at the middle, I bet you guys can see just by looking at this, what is this force equal to, and what is this force equal to, those tension forces. What do you guys say? Yeah, 250 and 250. That's 250 newtons and 250 newtons. Okay, you guys see that? Okay. Now, equilibrium. Remember, the sum of the forces in each direction is equal to 0 newtons. And for this example, maybe it'd be the y direction because those are all vertical forces. So a little subscript y. Okay. Furthermore, the sum of the torque is equal to 0, and that'd be Newton meters. And recently, just in the last few weeks, I used the second condition to solve problems like this. But say, what if you weren't hanging right at the middle, right? So something like that. So let's dig a bit more into this. From a torque point of view, why is this also consistent? Okay. Well, what you do is you have to pick a point as the pivot point. So let's say I do like this point right here, for example. Pick this as the pivot. Okay. Just it's kind of random. Okay. Now, relative to this point, there's going to be it looks like the scroll is trying to turn this whole thing clockwise, and this tension on the far end on the right is holding back counterclockwise. So you got a clockwise torque and a counterclockwise torque. I guess that's torque, right? Right. And those should be balanced. Hey, do you guys see how her weight is double this tension force? Right? It's a 2-to-1 ratio. But look at these distances. That's a 1-to-2 ratio. So she has twice. If you have twice the weight and half the distance, or vice versa, like half the force but twice the distance. Torque is R cross F. That's how that cancels out from a torque point of view. You see that? Okay. Now, the trickier question might be, what if she's not hanging in the middle? What if she's hanging like 3/4 over to the right? Okay. And that's where you really need the second condition to solve it, using the method that I showed you, like sum the torque about some pivot point. Okay. And the shortcut to this question was that whatever proportion she is over to the right side, the one that the rope that she's closer to is going to hold proportionally that much of her weight. For example, if she's 3/4 over to the right, 3/4 of her weight would be in this tension and only 1/4 in this tension. Okay. She's halfway, she's 50% the way over. It's a 50-50 split. Okay. That's but you get that by summing torque. All right. Friction is a force that always acts, especially if I'm talking about kinetic friction, like sliding friction. Doesn't that always act opposite of the object's motion? Like say an object is sliding across the surface. Like friction tries to slow things down. What is the maximum possible resultant from 2 newtons and 8 newtons? What do you guys think the maximum you can get is? How about 10? Here, I'll draw this one out. So you got 8 newtons and 2 newtons. Now, how do these tip to tail? You say you got a couple of people like pushing a box, and something like that. Whoops, 2. Okay. You guys see that would be the resultant would be 10 from the tail of the first guy to the tip of the last guy. Okay. You could do something like this. 8 newtons and 2 newtons, tip to tail. What would that resultant be equal to? You guys see 6, right? Or you could even do 8 newtons and 2 newtons. Say it's some angle, like a right angle. And if it is a right angle, you could do Pythagorean theorem to figure out the magnitude of that resultant. Right, Pythagorean theorem. Okay. So there's some different scenarios there. This next question. Okay, this next one's a bit involved. I'm gonna break out some paper and draw some stuff. We've got a 100 Newton lantern suspended by a pair of ropes with 120 degrees between them, which means that each rope is 60 degrees from the vertical. What is the tension in each rope? So, put a dot, no little paper. Have a downward vector, like this kind of big, and call this 100 newtons. And that represents the weight of some lantern. Maybe you've got like draw a lantern down here. It's all shiny. So 100 newtons of weight. And at this node right here, branches off to 2 supporting ropes. That way, and that's a little bit that way. Okay. And they each have a tension in them. Okay. And you were told some geometry stuff. You were told there's a 120-degree angle right here. Now, if this is 120 degrees, then what is this angle and this angle? What do you guys say? Would that also be 120 and 120? So 120, 120, 120 add up to 360 degrees, full circle. Okay. Okay, so I see that this problem has a special kind of symmetry to it. That's you can probably solve this based on symmetry. I think that's the intention of this question. Okay. I want to do more analysis on this, but I bet a lot of you guys are already seeing what the answer is. Can anybody tell me what the tension is in each one of those ropes? How many newtons of force? How about this? Let me change the context a bit. What if you had the exact same free body diagram, except a different story? What if we're up in a helicopter looking down on a field, and there's three guys playing three-way tug of war, and they have their ropes tied together in the middle? Who's going to win this three-way tug of war? And this guy's pulling south with 100 newtons. This guy's pulling kind of northwest-ish. This guy's pulling kind of northeast-ish. But you still have 320-degree angles. It's exactly radially symmetrical. Okay. Now, what is the force in each rope? 100. Would it be 100 newtons? Okay. Let's go back to the lantern hanging down. Same geometry, same physics, slightly different story. Yeah, the answer to this is 100 newtons. That's the answer to this question. 100 newtons this way, 100 newtons this way. Okay. Now, here's what I do is want to dig more into this bit. Let's say I introduce a Cartesian system with this pink ink. So I got a y-axis and an x-axis. So there's parallel to the ground, here's perpendicular ground, like parallel to gravity, okay. X-axis, y-axis. Now, that's just to help contextualize this. The weight is already pulling along one of those axes, it's already aligned to that system, but these other two ropes, I'm going to split those up into component vectors. The one pulling up to the left, what we're trying to solve for, we're trying to solve for this tension T. Okay. I will allow the simplification that based on symmetry, you can see that they would be the same. So, suppose you don't know what the tension is yet, but you just say, well, the left half looks like the right half, like mirror image, so I know they would be the same tension. So the one pulling up to the left, well, it's kind of pulling up, kind of pulling to the left. And the one pulling up to the right, well, that one's kind of pulling up, kind of pulling to the right, up to the left, up to the right. Isn't that true? Okay. Hey, see how I created a couple of right triangles up there? Component vectors. Okay. Who could tell me what is this angle right here? What's that angle? 60 degrees. Same story over here, 60 degrees. Okay. Ooh, I see right angle there. Right. Hey, this looks like a what triangle? 30, 60, 90. Yeah, this is 30 degrees right here. Same story over here. Okay. Now it's a little bit off the beat path of the way I'm going with this, but could be helpful to know. Right? 30, 60, 90 triangle. Where am I actually going with this, though? Right, so equilibrium conditions. The sum of the forces in the x direction equals 0 newtons. The sum of the forces in the y direction also equals 0 newtons. Okay? Now, that first condition in the x direction, that just means that this left component and this right component are exactly balancing each other out. Okay? I'm going to leave that aside for now, but look at this second condition. All the vertical stuff also has to zero out. That means this upward component and this upward component exactly have to balance out the weight, right? Okay, and if that's true, if the total weight is 100 newtons and these upward components are equal to each other, just based on symmetry, then, what is each of these components equal to? How many newtons? That number is 50. This is 50 newtons vertical, and this is 50 newtons vertical. Okay, just each of those components. Is that true? Is that? Okay. All right, and now we're actually really close to being able to answer this question. All right. So, you guys get that? Okay. I see some geometry. Let's go back to this right triangle. One of the legs of the right triangle, we're solving for the hypotenuse, and we know the angles. If you're playing out the 60-degree angle, because that's closer to what they gave us, right, then this leg of this triangle and this hypotenuse that we're solving for, with the 60-degree angle, have a what kind of relationship? Sine or cosine? See, this leg is adjacent to 60 degrees. That makes it cosine. Cosine. You guys remember SOHCAHTOA? Okay. Alternatively, if you want to play off the 30-degree angle and 50 newtons, that would be a sine relationship with the tension. But let's do 60 degrees in cosine. So cosine of 60 degrees is, well, that's adjacent over hypotenuse. That's 50 newtons divided by tension T. Okay. We do a double switch here. Cross multiply of T, divide down cosine of 60 degrees. Wouldn't the tension be equal to 50 newtons divided by cosine of 60 degrees? Is that true? Right, that's true. Cosine of 60 degrees. Does anybody happen to know what that is? Cosine 60 degrees. Hey, it's exactly a half. It's a little good tidbit to take out of high school, right? Hey, that's the same thing as sine of 30 degrees, because cosine 60 and sine 30 refer to the same side, don't they? Sine of 30 degrees, also a half. Right? You guys remember that? 50 newtons divided by half is 100 newtons, which you guys told me it was going to be a few minutes ago, but there you go. There's a more methodical way to also get to that answer through geometry. Right? Thanks for that. Which has more mass, a kilogram of feathers or a kilogram of iron? What do you guys say? Same mass, right? Each 1 kilogram. Maybe have different densities, different volumes, but same mass, same inertia, same gravity pull, same weight. Accelerations are produced by, well, when we talk about acceleration, in kinematic motion, we talked about this for a few weeks. We measured this, quantified it, said it's a rate change in velocity. Then a few weeks into class, we got to the reason of why anything accelerates. Nothing ever wants to speed up, slow down, change direction unless there's a what acting on it. Force. That's the answer. Force. Accelerations are caused by forces. Hey, I think we're starting to get into Newton's second law of motion right now. A lot of times it's written this way. Net force is equal to mass times acceleration. But I prefer a different version of Newton's second law of motion that looks like this. Acceleration is caused by a net force acting on some mass. These two lines say the same thing, a little bit different point of view, but I like this one more like cause and effect. Net force acting on a mass causes some acceleration. How does the acceleration of an object change in relation to its mass? Okay, so looking at these two variables. Guys, is there, say you do this. If you pump up the mass, bigger, 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 okay, what happens to acceleration? It gets what? Smaller. What is that relationship called? If one variable gets bigger, the other gets smaller, that's called a what relationship? Starts with an I. Inverse. That's an inverse relationship. That's the answer. Okay. I'll give you guys a story to attach to that. Suppose you got a tennis ball, sit next to a bowling ball, and you go across and kick the tennis ball with some force. Ping, flies across the room. Huge acceleration. Then you go to the bowling ball, put the exact same force on it. It barely rolls anywhere. Because the bowling ball has so much mass, it has very small acceleration. Okay. Another way that would tip off is back to this other form. Anytime two variables are multiplied together on the same side of the equation, also inverse relationship. Inverse relationship between mass and acceleration. When an object reaches terminal velocity, what is its acceleration equal to? Now, this one you do need to bring in air drag, which we ignored for the first few weeks of this class. Then we said, well, what if you do bring in air drag? Right, something speeds up, falling down a cliff faster, faster, faster. The air drag builds up more, more, more until the forces balance. The acceleration becomes 0. It reaches terminal velocity, goes down at constant velocity all the way down. Let me draw a story for you guys, a 3-part story. Let's go to the edge of the cliff. And I'm going to take this ball and drop this ball off this cliff. It's going to fall down, down, down. Okay. Let's have point A, point B, and point C. And we're going to look at the free body diagrams and furthermore the acceleration of the ball at each of these locations. Okay. I need a mass of this ball. Let's say mass is like 2 kilograms, which is more than 10 times as heavy as a baseball. But anyway, like 2 kilograms. So scenario A, scenario B, and scenario C. So get this ball. You could tell me, what is the weight of this ball in newtons, what is the weight in newtons? 20 newtons. Yeah, how'd you know that? Yeah, because gravity field is 10 meters per second squared on Earth. So mg, don't I almost always draw weight as in mass times gravity field? 2 kilograms times 10 meters per second squared, 20 newtons of weight. In fact, that would be true for all these scenarios, right? The weight of the baseball falling off the cliff is 20 every single snapshot. It's got 20 newtons of weight, 20 newtons of weight. Okay. Now, scenario A, let's say you just released the ball like a tenth of a second ago, and it's just starting to fall. So it isn't really facing any significant drag yet. This would be the whole story, wouldn't it? It'd just be that free body diagram. I'll say by the time you get to scenario B, now it's picked up some speed. I mentioned as a side note a few months back that air drag is proportional to the square of the speed. So anyway, let's say it builds up to like 4 newtons of air drag. And by the time you get to point C, now it's going faster, faster, faster. Air drag's building up more and more and more. Let's say it builds up all the way to 20 newtons of air drag. Something like that. So there's your 3 scenarios. Right? Follow-up question for each of those. Right, there's a free body diagram for each one of those. What is the acceleration? Remember, acceleration is net force acting on some mass. This is Newton's second law of motion. Okay? So for scenario A, wouldn't that be 20 newtons? Its weight would be the net force. It's the only force. It's free fall. Acting on 2 kilograms is, that's 10 meters per second squared. That's pure free fall right there, isn't it? For scenario A. How about scenario B? I've got, what is the net force scenario B? 16 newtons, right? 20 minus 4. So I got 16 newtons acting on the same 2 kilograms. That looks like 8 meters per second squared. Okay, so it's still accelerating. It's still speeding up. Just not as much as it was at the start. There's some air drag. Still speeding up, though. By the time you get to point C, what's the net force? 0 newtons acting on 2 kilograms. That's 0 meters per second squared. Does that mean the ball comes to a stop? No. That just means it's falling at constant velocity all the way down. It's done speeding up. Okay, just going to fall. Now, what is that velocity? Well, it's terminal velocity. That's terminal velocity at scenario C. Right? What is terminal velocity equal to? Right? Well, it depends on the shape of the object. If you have a small dense object, like a small dense ball, it's probably pretty fast. If I attached a parachute to that ball, I bet it'd be pretty slow. I mean, that's the point of a parachute, let you land pretty slow. But each of those, parachute or no parachute, would have the exact same free body diagram at terminal velocity, right? Whatever that worked out to. A book weighs 4 newtons. When held at rest in your hands, what is the net force on the book? What do you guys say? Book, center of mass, 4 newtons of weight. You hold up with your hands 4 newtons so that it's at rest. What's the net force on that book? 0 newtons. 0 newton net force. Girl pulls a 10 kilogram wagon with a constant force of 20 newtons. What's the acceleration? I'm going to sort of overkill this problem. Not too bad, though. Okay, wagon. They said the wagon has mass of 10 kilograms. What's the weight of that wagon? 100 newtons. If it's on a level surface, what's the normal force on that wagon? Also 100 newtons. Okay. Weight equals normal force equals. Okay. Now, if this girl's pulling with, let's say she's pulling forward, F sub pull is, what was it? 20 newtons. 20 newtons. Okay. Remember, the mass of this thing is 10 kilograms. That's how we do the weight, right? 10 kilograms times 10 meters per second squared. Okay. So Newton's second law of motion, acceleration is a net force acting on a total mass. Hey, it looks like the vertical stuff cancels out. So it looks like the pulling force is the net force. So we've got 20 Newton net force acting on 10 kilograms of mass. That wagon is going to speed up at 2 meters per second squared. There you go. It'll pick up 2 meters per second every second. if that wagon had a little speedometer needle on it, you go 0, 0, 2, 4, 6, 8 meters per second, right? It's going faster, faster, faster. An object has a constant mass. A constant force produces a constant what? Velocity or acceleration? A constant force produces a constant
Acceleration.
acceleration. Exactly. Okay. And then if something is accelerating, then by definition, it cannot have a constant velocity because there's a rate change of velocity, right? As long as the acceleration is not zero. Okay. Yeah, forces produce accelerations. Pressure is defined as what per what? Pressure. I bet you guys know at least one unit of pressure, maybe more than one unit of pressure. Pressure is equal to a ratio of something to something.
Force per area.
That's it. Yep. Force per unit area. Exactly. Now, in this class, since we use almost exclusively metric units, that would be newtons per square meter. And 1 Newton per square meter is also called 1 Pascal. You guys know that? And there's approximately 100,000 pascals of atmospheric pressure on us right now, which is pretty big. Right? If you guys are pumping up your bike tires with an American bike pump, then the gauge probably reads not in pascals, but in what? PSI. That'd be like pounds per square inch, which is also force per unit area, wouldn't it be? If the force acting on the cart doubles, what happens to acceleration? Acceleration is force acting on mass. If you double the force, what happens to acceleration? Wouldn't it also double? Is that a direct relationship? Tell you guys what, hopefully by this point in the class, you can see that. If you double the F, you're going to double the A. Okay. If not, one of the tools you can get for your mental toolkit out of a class like this is just make up some numbers and plug them in and try it out. So what if I put a 10 Newton force on a 1 kilogram mass? Is that going to accelerate at 1 meter per second squared? Okay. What if I double the force up to 20 newtons on the same mass? Now I'm getting, oops. Sorry, I messed up my math. Okay, 10 divided by 1 is 10. 20 divided by 1 is 20. And then the meters per second squared. So if you didn't see it before, I bet you see it now. Double the force, going to double the acceleration. You see that? Okay. Suppose a cart's being moved by a force. If suddenly a load is dumped in the cart so that the cart's mass doubles. What happens to the acceleration of the cart? You're pushing a grocery cart down the aisle with some force. It's speeding up. Right? Then you start dumping a bunch of groceries in there. Is that going to slow down the cart? Seems like it would, right? If you increase this mass, if you double the mass, what happens to the acceleration? Gets cut in half, right? Now, if it was an inverse square law, like gravity pull, that would be a quarter. But here it's just plain inverse. Yeah, double the mass to get half the acceleration. And tell you what, let's do the same little trick that we did over here. If you put 10 newtons on 1 kilogram, that will result in 10 meters per second squared. What if you keep the same force, but you double the mass? You guys see that now you're going to get down to 5 meters per second squared. So by doubling the mass from 1 to 2 kilograms, you got half the acceleration. Okay. You might be able to just pick that out from the formula anyway. A 20 Newton object faces 4 newtons of air resistance. What is the net force on the object? We talked about that already. It's 20 minus 4 is 16 newtons net force. And works out like that. I saw that one already. A 6 Newton falling object encounters 6 newtons of air resistance. What's the net force? 0 newtons. Hey, that's equilibrium. It will go down at constant velocity called terminal velocity. High school student hits a nail with a hammer. During the collision, there's a force. Is there a force on the nail from the hammer? Yeah. Is there a force on the hammer back from the nail? Yes. Which force is bigger though? They're equal for every force there's in. Equal and opposite reactive force. We're up to Newton's third law of motion. Okay. So action and reaction pairs. Forces forces between two interacting objects are always equal in magnitude, opposite direction. It's just a law of the universe. As a ball falls, the action force, look, they're using Newton's third law of language. The action force is the pull of Earth's mass on the ball. It's called gravitational mass. What is the reaction force? Let's draw this out. Earth, ball. Is the Earth pulling on the ball? Yep. Suppose it's like 20 newtons of gravity force. Okay. What's the reaction force to that? The ball pulling on the Earth. Ooh. Is it also with 20 newtons though? Sure is. Okay. Hold on a minute. If this is equal opposite forces, I see that ball accelerating at 10 meters per second squared. I see the Earth barely moving at all. Why? Because the Earth has so much mass, so much inertia. Right? More mass, less acceleration for the same force. Unfortunate bug. Got a pair of questions right here. Unfortunate bug splatters against the windshield of a moving car. Compared to the force of the car on the bug, the force of the bug on the car is what? The same force. But the follow-up question is, compared to the deceleration of the car, the deceleration of the bug, that's kind of a colloquial way to say that. Let's say like the rate change motion of the, compared to the rate change motion of the car, the rate change motion of the bug is what? It's much what? Larger, much larger. Because, kick back to Newton's second law of motion, acceleration is net force on total mass. Now remember, same force on the bug as on the car during that interaction. Bam. But huge mass on the car, very small acceleration of the car. Okay? The car barely notices. It's like, oh. Now maybe if you ran into like a million bugs, like that might slow down the car a little bit, but the G is all right. But the bug, such tiny mass, huge change of motion for the bug. All right, bell rings in about 10 seconds here, so have to hit a pause point. But when I see you guys on Monday, I've got a couple more force examples to do with you, and then we'll continue that review. You guys have a good weekend.